collaboration based on previous work, whatever, sponsors. So yeah, sorry about that. So yeah, we sat down, discussed the features, and these are some of the most important features we felt like. So this gripping by minimizing the relative movement, having at least 3 fingers for stability. And then RSP also suggested that they wanted it to be electromechanically actuated because they see it as most of the industry use pneumatic tools today. And it's a very expensive system to keep running, and they want to see if the further developments could be made and maybe replace them with electric motors and such. So yeah, from that we derived our own project goals, which Dennis here will speak about right now.
Hello. So let's see, I'm gonna get this straight. So as you saw, we had the project goals defined by the stakeholder and the sponsors. These had to be clearly redefined within the project to make the list of functions needed more rational for us in the project. So we listed them as numerical goals. Let's see. So as I said, yeah, they were listed as goals within the project. So for example, we have PG2, PG10, and PG11 here. These are the same requirements as, or project goals that Hannes told you, but defined for us within the project so we can understand it. It might be more technical or whatnot. From these project goals, there were derived requirements. So to make it easier, I structured the requirements in 3 different levels, a hierarchy. So the top level requirements were called high level requirements. These describe the system on a very abstract, in an abstract way. These were based on user need, performance, and safety and such. And high-level requirements were categorized in 3 different categories: functional requirements, non-functional requirements, and safety requirements. The functional requirements and non-functional came from the project goals, and the safety came from the safety analysis manager. The mid-tier requirements were the technical requirements, where specific technical solutions for the system were described. And underneath that, we have the module requirements. So each component has a separate module. So say a technical requirement describes a thing, and then it results in a component. And that component needs to be specified in some way. Voltages and such. For example, the power distribution board, which is a part in the hardware, had voltages specified, buses and such, and so forth. All these requirements were elicited, and this eliciting process was mainly from the project specification, which had the top goals and basically some requirements already defined, but we had to define some own requirements. And this was conducted within the team, with the hardware, software team, also together with the other managers, quality and safety, which had a say in some high-level requirements. What were the technical needs, and what is really reasonable within the project time? So all this had to be taken into account when we wrote the requirements. And also we had to prioritize them depending on time it took and cost to implement it. And this priority was defined in 1, 2, 3, which one was critical for the system. So example, you have a hand which grips things, you need actuators, you need hardware to make it work. So critical features of the system were categorized as priority 1. Not so important stuff like secondary safety requirements where you define safety areas and such, which isn't critical for the system development at the time, were categorized as not important or priority number 3. So here's an example of the requirement chain. So this requirement describes the on and off switch, basically. So the high-level requirement states that there should be a hardware input to toggle the gripper on and off. And this cascades down the hierarchy to the lower sections of the requirements. So what that resulted in the end was the 24-volt bus, which is the input, shall have a connector in series, which basically toggles the power on and off. And the housing need a slot for it, so you can put it somewhere on the physical product. And this is the emergency stop button. You can see high-level requirement comes from the safety manager, a functional requirement, and then it goes down the order or hierarchy. The safety of the system was the safety development of the system was conducted by the safety manager, and he implemented a safety management system. The SMS is a top-down approach to manage safety risk created by the safety manager. The primary function of the SMS were identification of safety issues, risk assessments, and risk mitigation. And in this, you made a hazard identification and analysis, where the hazard identification and analysis was part of the process used to evaluate if the situation or component within the system may potentially cause harm to user, environment, and such. And the identification of the hazards took place by reviewing, studying the system step by step, identifying hazards. These were then analyzed to find causes, effect, consequences. The system was used to find suitable, or the results were used to find suitable safety solutions for the system. For example, the emergency stop button and some hardware redundancy or something. Things like that. The assessments were conducted to find the hazards of the system, and the next step was hazard analysis this was conducted by using some known tools like the PHL, FMEA, PHA, and HACCP. By knowing the nature of the danger, it's easier to safeguard and find a solution to mitigate the hazard. So let's see. There was also a risk assessment done. The risk was evaluated in a risk assessment where the severity of the consequences and occurrence were assessed. This assessment determines if the risk is acceptable or need further reduction. These risks were ranked, and actions in a development standpoint were listed under this. Here's an example of the PHL, the FMEA, PHA, and HACCP, and the risk assessment. Yeah. So if there was a serious risk, we needed to investigate the process and implement an immediate counteraction for this risk. Example, if something runs away, you need to, say a motor hangs or something, presses, somebody get caught in it, you need an emergency stop button. So the solution was the stop button, basically. Medium risk. The process can keep going, develop a control plan, and implement it as soon as possible. So there was it's not urgent, but it has to be assessed. Low risk. The process can keep going, monitor the process regularly, and the control plan shall be investigated. So you need to investigate if you need a solution or if it's acceptable in the end products. So we had a quality manager also, and the quality management was used to ensure that software and hardware designs follow the plan according to standards and documents defined early in the stage. Quality assurance covered the entire project, ensured that the processes have been sufficiently performed and adhered to standards. Pre-plan reviews to prove that work is being carried out and regularly were carried out regularly according to plan. Quality control was used to review the quality of the product, and the inspections were conducted to identify problems and defects that needed corrections. Quality improvements, there was an underlying quality thing in the background that you can always improve stuff if it doesn't work. So we had a hardware situation where we had some screws that had to be inserted in some way, and it didn't work in the end. You could do it while you develop the product, but in the end, when you have a product, you don't want that solution because it complicates things for the user. So we had to improve this, and it was done. Total quality management, TQM, can be summarized as a management system for customer-focused organization that involves all employees in a continual improvement. Uses strategy, data, and effective communications to integrate the quality discipline in the culture and activities of the organization, which was one of the tools used by the quality manager. The Six Sigma was used in the beginning of the project, and the method, specific method, was DMADV, which stands for Define, Measure, Analyze, Design, and Verify. This method aims to create a high-quality product, keeping in mind customer requirements at every stage of the process. And also, finally, validation and verification. The validation work was based on the definition: are we building the right product for the customer needs? While the verification work was based on the definition: did we build the product correctly? Validation work have been conducted in order to compare the achievements to the specified requirements and project goals, meaning find bugs and errors and stuff like that in the architecture and the design. Verification work has been conducted in order to ensure that the product satisfies the expectation from the product owner and show that the delivered product satisfied the project requirements. So, validation methods used was a requirement review, where the aim was to review the rationale of the requirements and the goals, and if the validation criteria fulfill or not. Analysis of work was done in order to ensure that we are building the right product. Validation criteria were also developed and followed during the analysis. The aim of the analysis was to find possible bugs or errors and ensuring we are on the right path of development towards building the correct product. Oh, sorry. Verification method used were a traceability matrix that connects requirements to design decisions and how they shall be verified. Architecture review was also a part of the traceability matrix. Final tests were conducted by a test engineer, as the BMV manager unfortunately got sick during that stage of the project. But he supplied them with manuals, test manuals and stuff like that. And these results were then documented in accordance to the DMV plan. And next up is hardware. Sonny.
Ja. Kan ni höra mig?
Yeah.
Okay. For the hardware, the initial concept of the gripper consists of 3 choices: finger system, the number of fingers, and how many degrees of freedom are needed. For the finger system, we have chosen the lever-driven, fully actuated method. A fully actuated finger has an actuator for each degree of freedom. This method has good dexterity, but it is limited in power by the upper actuator. This can be solved by adding lever system. See the pictures here. For a number of the fingers, we have decided to use 3. This is because of 3 fingers are the minimum number of the fingers required to achieve stable grasp, and the minimum amount of finger we should implement it in this project according to the requirement. 4 or more fingers can provide more actuating power, but it will increase the cost, power demand, and execution time. The budget and time in this project are limited. If we can design the finger stronger and larger to increase the capability to lift a heavier object, then 3-finger solution is able to complete the task. The degree of freedom for each finger we have chosen to be 2, since it is enough to envelope objects as well as perform a parallel grip. More degree of freedom can improve dexterity, flexibility, stability, and adaptability, but it becomes impractical with fully actuated gripper, since the mechanical complexity and the cost will increase. As we mentioned before, the budget and time limit the design, so 2 degrees of freedom is used here. The next slide. The hardware architecture shows how the hardware design looks like. The gripper contains 1 fixed finger, 2 rotating fingers that can rotate up to 90 degrees. Each finger has 2 phalanges, distal phalanx and a proximal phalanx. Each phalanx actuated by 1 servo motor. Distal phalanx contains 1 optical sensor, 2 proximity sensors, while proximal phalanx contains only 1 optical sensor. The fingers are attached to the palm, which is equipped with a proximity sensor, a camera, and a line laser for object detection and shape estimation. For the supporting electronics are located under the palm in an electrical housing. The housing envelopes and protects all electronics, such as microcontrollers, power distribution board, and relay. The rest of the components will be placed at the side of the housing. For the hardware flowchart, the next slide. The hardware is divided in mechanic hardware and electronic hardware. See the flowchart here in the right. Mechanic hardware consists of numerical analysis and the gripper design, such as fingers, palm, housing. Electronic hardware focuses on developing the electrical system, such as sensors and PDB. The works are planned to do in parallel. The integration takes place in the last step when both parts are finished. Troubleshooting and the tests will be applied before we hand it in over to the software team. Now, Arden will present the mechanical hardware.
Yeah. So we started the design of the hardware by developing a numerical model for the gripper. Purpose of this model is to define the length of the phalanges and the levers. The numerical design is divided into 3 parts, creating a kinematic model to get the finger position and angles based on the position of the actuators. Then do a static analysis to see how much theoretical force can be exerted from this finger configuration, and finally define a suitable length based on the system and objects to grasp. Jump to next slide. This is the same picture of the kinematic model. We can move forward. Next slide, yes, thank you. This is the static figure of static analysis, and it's used to get the counteracting force Fn, representing the force the finger is able to exert on an object. Next slide. This graph represents the maximum theoretical force 1 finger can exert for a given gripper opening width. It utilizes the kinematic and static model as well as implement a friction and the safety factor to score some objects represented here as red circles. If the objects are beneath the blue line, they can be grasped and hold on to. The max object represents an 100 millimeter cube that weighs about 3 kilograms. By using this plot, lengths for the levers and phalanges can be evaluated and chosen for the system, for the gripper. Next slide, please. Next slide. Tado. Yes. Construction. The gripper was designed in SolidWorks. All parts such as the fingers, motors, and electronics, and everything was have a digital representation used here. Next slide. The finger consists of 3 or 4 parts: proximal phalange, distal phalange, A lever, and B lever. The parts are designed to be compact and be fitted to the servo motors. The B lever is indicated in yellow, is a shape to accommodate the presence of the servo motor and one when the finger is brought to the most forward position. Gripping. Next slide. These are the motor arrangements. There's 2 types. 1 2 degrees of freedom and 1 3 degrees of freedom for the rotating fingers. They're built of standard components for the servo motors and the assembled. Take next slide. Yes, this is the palm of the gripper, showing the figure to the left. And the motor fixture to the right used to connect all the motor arrangements and act as a connecting point between the fingers, the palm, and the rest of the electrical housing. Next slide. This is the electrical housing. The palm and motor fixture do not have a space to allocate for all the electronics, so it's placed in an electrical housing box beneath the gripper. It is designed by arranging the electronics in a neat package in SolidWorks and adding a shell around it. The left figure shows the shell sides, and the right figure is a shell completed with all the electronics and top and bottom lid fitted. And finally, we have construction. Otto? Yes, thank you. This figure shows the gripper fully assembled. Most of it is printed in PLA, except for the shell that is for the electrical housing that is constructed out of acrylic plastic, which is also make it possible to view the internal system. The green surface on the fingers are rubber to increase the friction. Yes, and that's all from me. Next over to who's next? Tado.
Yes, hello, my name is Dalibor Cholic, and I've worked with the electronics part within the AIGripper project. I will briefly go through the main components chosen for this project and then continue with the electrical design. But first, I just want to show the general design of the electronic system. And as you can see, everything is connected through the PDB. So it's kind of like the heart of the electronic system. So the Nucleo H743ZI2 microcontroller was chosen basically because it's cheap and it has all the necessary communication ports as SPI, UART, and I2C needed. But the most important part why we chose this one is the STM32Cube ID, which essentially allows the programmer to easily program because no peripherals are needed to be set, and the code is generated automatically. Then we have the
NVIDIA Jetson Nano, which is a powerful single board computer, and it's relatively cheap. It can run multiple neural networks in parallel, which is great for image classification and object detection and segmentation and so on. And it communicates with the microcontroller via I2C. Then for the servo motors, I think these were a solid choice since they were relatively cheap and had a sufficient torque. These motors were also used in 2 previous thesis works here at MDH. And since we needed to use 8 servo motors for the gripper and also have 2 spare ones, it meant that they could not be so expensive. These smart servo motors can send information about position, load, temperature, and more. So this makes it a great choice for a self-adapting gripper. And the motors use half-duplex communication, which means that they can only send information in one direction through one TX line. And to enable us to receive this information, like position, for example, we needed to have a 3-state buffer, which is essentially a full duplex to half duplex converter. So it basically switches between the TX and RX parts, so we can receive information on that same line. Moving on, we have the PMV3360 optical sensor, which actually is a high-end gaming sensor used in gaming mouse. And in this project, we utilized the high-speed motion detection of this sensor in order to detect movement in the XY plane, and thus knowing if the grasped object is slipping or not. And the sensor communicates via 4-wire SPI communication. Then we have the proximity sensor, which is a VL6180X, and it's a really small sensor capable of measuring distances from 0 to 10 centimeters with high accuracy. It is independent of object reflectance due to the technology used, and that technology is called time of flight, which means that the sensor measures the time it takes for the light to, from being emitted to received, just the time it takes for the light basically to bounce back. And this is much better than distance sensors, which measures the amount of light that's being reflected, as it is significantly influenced by color and surface of the object. And the sensor also has some built-in filters, which reduces the need for any extra circuitry. Moving on to the design of the PDB. The PDB was designed to distribute power to various components, but also to handle sensor data and communication between sensors, motors, and the Jetson Nano. The PDB is based on a 4-layer design, where the top and bottom layers are the signal layers, and the 2 remaining layers are a ground plane and a power plane. The thought with this was to eliminate potential disturbances by separating the power and ground plane from the signal planes. And as seen here in the PDB, we also have the connectors for all the motors, the optical sensors, and the proximity sensors. And here, as I said, the PDB was designed to distribute power. So we have an input power here at 24 volts, which is then converted to 12 volt, 5 volt, and 3.3 volt. And this is used to power these different components. For example, the 12 volt is used to power up the nucleo, which is placed here, as you can see here. Then we have this larger this DC converter, and this also converts 24 volt into 12 volts, but it can deliver up to 10 ampere, since we have a total of 8 servo motors, and they are each rated at 1.5 amps at max torque. The large DC converter is also isolated, meaning that the plus and minus on the input side here are not the same as the plus and minus on this side. And this means that we can isolate this whole part of the PDB from the rest of the circuit. And this is to eliminate some potential disturbances from the motors. So moving on, we can see the blue part here. That's the whole ground plane. And within these black borders, we can see the isolated ground. So it's separated from the rest of the system. Then we have the optical sensor PCB, and this is just a simple breakout board for this PMV3360 sensor. And it was made simply to have an easy connection when integrating it with the gripper. The same for the proximity sensor PCB. It was also made to enable easy connections when integrating the gripper. And this PCB is very small. At least in my opinion, it's 18 times 8 millimeters. And the sensor here in the middle is even smaller at 4.8 times 2.8 millimeters. And this made the soldering process extremely hard. And I will talk more about that later on in the presentation. The gripper is equipped with some simple safety solutions. We have 2 emergency stops, one simple stop button, as you can see here, and then a mechanical relay. Both these emergency stops cut the power to the motors, which makes them basically rotate freely. So if a human was to be grasped by this gripper, then the emergency stop button could be pressed, and the motors would basically release the power that they have. There's also a key operated switch which needs to be turned in order to turn the gripper on, and then a green light will be lit, showing people around the gripper that it is on, basically. And as a last safety measure, not so much for humans but for the electronics, we have a cooling fan which can replace the heated air within the electronical housing with fresh air from outside. So some results. The electronics of the gripper worked as intended with some modifications, which I will go through. We had some errors with the PDB, and the first thing is the isolated ground. This caused some problem when we tried to send data from the nucleo, basically from the microcontroller to the motors. They had different grounds, and this caused a ground potential difference between the nucleo and the motors. So the signals couldn't be read correctly by the motors. And this was solved by simply connecting the 2 ground planes together. The second problem was the footprint of the microcontroller. Here in red, you can see all the faulty connections. And the problem was that they were all shifted 1 step to the left. So in order to solve this, we had to move the microcontroller 1 step to the right, and then connect these green ones, which were correct from the beginning, with cables. Then we have had a small problem with the optical sensor PCB. This VDD IO is basically the power for the internal IO of the sensor. And this was included in the schematic, but then forgotten in the PCB design. So we had to connect 2 cables to compensate for this. And then lastly, as I said, I would go through the soldering process. As you can see, the sensor PCB is very small. This is just a normal metallic clip. And you can see it's very small relative to that. And the pad size, which we can see here, it's only 0.2 millimeters between the soldering pads. So it was very difficult to solder the component, or components, I should say. And we never got this sensor PCB to work. And that's mostly due to the soldering process. And now Martin will continue with the software. Thank you.
Yeah, let's go, Samuel. The gripper has 3 modes during the operation of grasping objects. First, a mode called pre-shape is used to estimating the best achievable grasp. Then approach to make sure that the contact between the fingers and the objects is confirmed. And then slip node for adjusting the applied force so that the grasp is secured. Next slide. The pre-shape is to find a grasp configuration when the object is detected but not within reach. The first step of the pre-shape is to get the surface of the object and the size of the object, then to get the signature of the object, and lastly to estimate the desired gripping, if the desired gripping configuration is possible to establish. Next slide. To estimate the size of an object, the relationship shown in the figure is used because the 2 triangles have the same ratio. If 3 of these variables are known, the 4th can be calculated. To get the distance to the object, one distance sensor is placed beside the camera. The focal length in pixels of the camera was calculating by using the camera calibration app in MATLAB. And the pixel height of the object can be calculated directly after image processing. Next slide, Samuel. To give to grasp an object, there is a huge amount of possible ways to do it. So there must be some kind of priority selection made to choose a grasp. In this project, we used signature to give a priority for the grasp configuration in each finger. In image processing, a signature is a method to reduce an object from 2 dimensions to 1 dimension. It is a kind of feature extraction that compromises the information of an object. To make a signature, you need at least 2 features and then make a relationship between them. The type of signature that was used in this project was the radius dependent on the angle. In this image, you can see an example of how this kind of signature looks like on a circle and a square. Since the circle has the same radius in all the directions, it will become a straight line. The square has 4 corners, what will represent maximum points, and the middle of each line will be minimum points because it's closest to the center. The difference between this example and how we do it is that we set the target point in the middle of the image instead of the middle of the object. The signature is set to the priority of which angle the rotating finger should have. The target point with the lowest signature get the highest priority. Since the thumb cannot rotate, it will not have any priority list of the configurations. Here is an example of the signature for a box. The black dot represents the target point or the center of the camera, and the red dots represent the gripping points with the highest priority for each finger. The circles is suggesting grasping points with a scale from blue to yellow. The blue one is 0 degrees and the yellow one is 359 degrees. The rotating fingers have a limit of how much they can rotate. It explains why the red dot is not the closest of the suggesting gripping points. Next slide. When the priority list is made, it must be checked that the gripping points is in the workspace for the fingers and that it has an acceptable orientation. We are not going to explain how it is done since we have more important things to mention. So now over to Martin.
Okay, can you hear me?
Yes.
Yeah, okay. I'm just gonna activate the camera. And the camera is working.
Yeah.
Okay, good. So to talk about the approach section, we use the optical sensors in the fingers, but only work within 3 millimeters, which is determined from reading the datasheet. So that means that the fingers need to be very close to the object before we can enter the slip prevention algorithm. So this means we need to have an intermediate step called approach, where we close the fingers until we have contact. So one way to solve this is to have, for the close proximity, is to have a real precise pre-shape estimation. And this would include making a precise segmentation of the object, getting a precise size of the object, and a precise position of the object. But this would require way too much work, so instead this intermediate step is used. So instead of positioning the fingers in the optimal position, we inject an offset, and then we use the distance sensors in the fingers in order to have a feedback, so we can close the fingers until we have close enough relation with the object so we can enter the next algorithm. This is not really implemented since the proximity sensors didn't get into a functional state, but it was emulated, so we can guess the performance. Yes. So the next step is the slip prevention, which we call slip knot. We use 2 different methods for this primarily. We had more of interest that we investigated, but didn't really have time to evaluate. So when detecting slippage, we have 2 events that we can identify. One is gross slippage, which is the object the surfaces are slipping towards all the fingers simultaneously. And for that, we have the related works of the previous theses, where a threshold is used and compared to the magnitude of the average of the optical sensors. And if the threshold is exceeded, it is the force is increased to compensate and try to stabilize the grasp. And this threshold is hard-coded. It should be tweaked for better performance, but it is functional. And the next method is based on covariance between the optical sensors, where we calculate the covariance between all sensor pairs for the optical sensors. And if there are a slippage occurring for one finger or for one sensor, we can detect it and prevent the gross slippage before it occurs. So it's kind of preemptive force compensation. And this covariance calculation is made over a predefined time window. So we take a couple of samples, and this should also be investigated further. Let's see. Yes, communication. In this gripping tool, it would be as it would be attached to an industrial robot, the user might need some sort of interface that can be used without being close to the gripper for safety reasons, for example. It also makes it possible to get status messages from the gripper, to communicate with the user, and smartphone application, which communicates with the Jetson Nano over a Bluetooth, is implemented. For this communication between the boards, as stated previously, we use I2C. And for the sensors, we use I2C and SPI respectively. And as also mentioned, and the motors, we communicate over UART in the Nucleo board. And it's similar to one wire, but they use their own kind of protocol from the developer. So we also had to implement a functional API for this protocol. Next slide. And for the smartphone application over Bluetooth, the ability of the user or client to be able to easily stop or start the gripper and instruct the gripper when it's time to release an object is desirable for human-robot interaction. And the Bluetooth was chosen as the interface between the user and gripper because it is wireless, easy to use, and uses direct communication, which simplifies the setup. During this project, we used a template application on a smartphone to control the gripper and get the current status back, so to say. And here to the right, you can see an image of the application used. We have we connect the phone to the gripper and can send two commands, start and stop, and in the window below you can see the status that you send a command and then you get feedback if it is transmitted properly within the gripper. This made it possible to test the gripper on different places without always connecting a computer through a USB to send the controller commands. Next slide. And as briefly mentioned before, between these microcontroller units, we use I2C to communicate, where the Jetson Nano acts as the master and the Nucleo as the slave in the communication setup. And this means that the Jetson Nano allocates time slots for when the Nucleo is allowed to transmit. And the most of the sensors is connected to the Nucleo board. So we also need to transfer that information between the boards. And since the Jetson Nano makes the most behavioral decisions of the gripper, it sends the control commands and user commands to the Nucleo. And the Nucleo uses that data to control the motors and provide the Jetson Nano with the respective sensor readings and current motor positions. Jetson Nano is the basic software system is set up as you can see in the picture, where we have a central communication handle which handles the Bluetooth communication to the user. It handles the I2C to the Nucleo, and it handles the control behavioral decision making within the Nano based on the image processing and interconnected with the user instructions. It also calculates the heavy algorithm since it's much more powerful and to not impact the performance of the motor controller. Next slide. The Nucleo reads the sensors and receives the commands from the Jetson Nano, which it then uses for the controlling system. It is based in the system is designed relative to the image shown in this section as well, where we have a central communication task which sends the instructions from the user and the behavioral controller to the motor controller, which then updates the motor positions if depending on which controller is control state is transmitted. And it also feeds back the information so that we can have redundancy within the system and check if it is what we expect it to be. Next one.
Okay. So now I'm going to talk about how we segment out an object in an image. For this project, we use an easy way of doing it by just segmenting out color. So the first thing we started doing is we converted the image from RGB to HSV. This because it makes it a lot easier to do a color segmentation because of how HSV is defined. So when you use, it stands for hue, saturation, and value. And by doing the HSV, we can set up this table you can see in the image. So we define all the pixels to be one of the primary colors, white or black. So you can see in the image, if, for example, if we have a pixel of hue 55, a saturation of 40, and a value of 60, we would classify that pixel as a yellow pixel. And then we assume that the object is in the center of the image, just to simplify things. So we take a cluster of pixels in the middle to determine what color the object is. And then we make a bitmap that only contains a binary map that only contains that color. So it might look like something like this in the first image when we have done the binary. So all of the red pixels gets filled in and becomes a 1 in the binary image. Then we do some filtering. So we fill up all the holes. We take out segments, maybe if it's some fragments of pixels in the background. We filter that out. And then what we end up is this last picture. And that's what we send back to the pre-shape stage that we already been explaining. So with this, we can determine how we should grip the object. So the results. The pre-shape worked successfully in some circumstances. We tested with a blue cup, a white cup, a small red box, and a black battery, and a green box and a red box. And we tried, see if it would turn the gripper so it would come in a position where it could grip it. Because of the faulty distance sensor and time constraints, the approach and size estimation has not been tested really in the real world scenario. We have tested some in MATLAB, only in theory, and by that it seems to work, but it needs to be more tested. The anti-slip system worked. We tried to replace objects inside the gripper and pull data, and we can see that the gripper is grabbing it harder to prevent the slippage. Then we can see we measured some of our functions in this table to just see where our bottleneck in the systems are. Now I have some videos. I don't know if they're gonna play. No, I don't think they're gonna play. Yeah, maybe here. You think it's much easier to play a video on? I think we're short on time, so maybe. Oh, here we go. So here's the first video. You see we can place we place the box in front of the gripper. Then we press start in the app. Then we can see that it moves the fingers and tries to approximate where the box is. So if we move the box into this position now, it will try to grab it. And you can see here in the end, we press stop and they go back to the default position. Then the next video, it's basically the same thing. Just we have a white cup here. Turn out the audio. You can see that it tries to take it on the top and bottom of the cup, just because it thinks it's the best position. And you see we press stop and it goes back to the default position. Now it's we're going to go over to Dennis with results in respect to requirements.
Yes, so going back to the original project goals or requirements that were listed in the beginning, we can see the results in the test cases. Have the key switch been implemented and function as expected? The related requirements are listed, the test IDs are listed here, and the method for testing also. So it has been inspected, it has been tested functionally, so you test the function physically, and the result for this was passed. It's an expected result. And non-functional, which was implemented, was cooling. As the fan in the housing been implemented basically, and it was conducted by inspection in 2 of the cases and 1 run test, and all tests passed. And here we have the next we have the emergency stop button has been implemented and function as expected. And yes, it has, but as we had a redundancy in the emergency stop function, it did not pass as the hardware-based emergency stop worked, but the software-based emergency stop did not work as it couldn't be implemented. But overall, the requirement itself is satisfied except the redundancy requirements, which was not a prior to 1 requirement. Yes. Related work. Future work.
Yeah, so for the mechanical improvements, it would be good to optimize the finger lengths to get more dexterity and to actuate more power. And find a better solution for rotating fingers to provide more structural support. Or add the mechanical structures to the gripper to strengthen the parts. That's all I could Dodo?
Yes, so I described these errors we had with the electronics, and I of course have some suggestions. So the first one is with the proximity sensor. That's the one that was really small. I would suggest to not make your own PCB. Instead buy a finished one. Adafruit has one that is yeah, it's a nice solution, pretty small still, but it has a voltage regulator as well, so it can be run at 5 volts instead of 2.7, which means that we can get rid of one of these DC converters. Then for the optical sensor PCB, just don't forget to include the VDD IO and the LED power as I did. Otherwise, it's a good solution to make these PCBs yourself. Then for the PDB, I would suggest to keep the isolated ground, but of course, include some optocouplers or a capacitive isolation so that we don't jumps between these different ground planes. And of course, the footprint of the Nucleo needs to be fixed. And that's, I would suggest to, if possible, to print out this PCB at the school first in order to see if the footprint actually fits, as there isn't any information about how these footprints, there's no dimensions, so to say. Yes.
Yes. So some software improvements. I would suggest to improve the state machines for the control thread in the Jetson Nano, so control all the when it's going to what stage in the program. Then further testing on some algorithms needs to be done, mainly the size estimation, slip knot, and approach. And then I implement a segmentation algorithm can detect a further range of objects, because now it's limited. Now we have a color segmentation algorithm. It needs to be unicolor and stuff, and it should be good to have a completely unknown object. And that's it. So